Well, our next speaker is Simon White from NPA, and he's going to tell us about simulation constraints on the nature of dark matter.
Well, it won't have escaped your notice that in Orish's talk, all the objects he was using to try and constrain our cosmological parameters or cosmology were based on galaxies and galaxy halos, that is, on nonlinear objects. And one of the main threads in his talk was how to evade the problems that this causes. So for a long time now, one of the ways to test how well, how nonlinear effects in structure formation distort the information we'd like to get from the early universe has been to look at simulations. And this actually goes back a long way. I think the first simulations that I know of that were published to understand how clustering grows into the nonlinear regime were actually in this very famous paper. If you look at the abstract in Press and Schechter, you'll see they base their conclusions on the results of numerical experiments based on 1,000 particle n-body integrations. And what they did was they put 1,000 bodies inside a sphere, solved the Newtonian equations of motion, and bounced the particles off the outside of the sphere when they hit it, and used that to have their cosmological boundary conditions. And what they found, so they looked at the strength of structure. So this is the 80th percentile mass. So this is the mass of an object, so that 20% of the mass is in objects bigger than this, the function of the expansion factor of their sphere. They had two different initial conditions. They put the galaxies down just in a Poisson distribution. They put down a mesh and put a galaxy at random in each cell of the mesh, which gave them something which is more uniform than Poisson. So their initial conditions were either white noise or flatter than white noise. And what they saw in the white noise case, they got a growth here, which is what they predicted from their theory, which is what everybody remembers this paper for now. And what they got in the case where they put down something which was redder, and so less structure on large scales, was it started following what they expected, and then it went steeper. So if you actually look at the conclusions of their paper, they propose that actually the mass spectrum you get at late times becomes self-similar independent of the initial spectrum of fluctuations. Okay? And this is because what they saw were new nonlinear effects in their simulations where condensations bootstrap their way up faster than linear theory. So we know now that's actually incorrect. So the basic conclusion of the paper, which was based on their simulations, was not correct. We now know that in fact the large scale is follow linear theory, also in the case that they simulated. So we learned several things from this. What everyone now remembers the paper for was the linear theory calculation they did, which was correct, or at least gives the right behavior. And what you learn is that you have to be very careful with your numerical simulations. You shouldn't believe them too much. So with time, what happened was for a long time, this was in the 1970s, right? So we didn't have an idea what the initial conditions should look like. And so simulations were used primarily to try and understand the process. So here's another example, again, of simulations from white noise initial conditions to see how the nonlinear clustering process worked. This is in Eustathio and Eastwood. By this stage, they could have 20,000 particles. They knew how to put periodic boundary conditions so you didn't have a sphere at the edge. The studies were still focused on nonlinear growth from these very idealized initial conditions, just Poisson noise in this case. Or here's a Soviet calculation from the same time by Klippin and Shandarin, which took white noise and then truncated the power spectrum at the high frequency end to throw away all high frequency noise. So it's a completely sharp cutoff. And they were trying to look at adiabatic theories for structure formation to understand how the suppression of power on small scales might affect large scale structure, but they implemented this just by taking white noise and then zero. And they were looking for coherence in their distribution, which is actually here, although you can't see it because the graphics at the time, they couldn't plot all the points. There are only 10% of the points are shown in the plot. If you look at regions with all the points, then you can see the filaments joining things. And there was this nice cosmic chicken, which I remember seeing when I was a graduate student, postdoc, which convinced me that there really was more coherence in these things. So already there was some idea of how the power spectrum would influence the structure. But the real breakthrough came as a result of another incorrect experiment, which was the apparent measurement of a 30 eV mass from the neutrino in 1980 from a Russian experiment on tritium decay, for the endpoint decay. And they appeared to get a measurement for 30 eV, which was then known that this would be enough to provide the dark matter. So although people had thought about neutrino dark matter before, they started to take it very seriously at this point. And then this stimulated proper calculations of what the linear transfer function should be coming out of the early universe. And so here are examples from the big paper by Bond and Saleh in 1983. They have now a prediction for the power spectrum, in the linear power spectrum at late times for massive neutrinos, where now there's a relation between the characteristic scale here and the mass of the particle, which translates to the characteristic scale here and the cosmological parameters, the density of the universe. So now there's actually a precise initial condition which corresponds to a physical model. So at this point, you can start to test the physical model. And at the same time, they thought, well, why stop with neutrinos? Other kinds of particles can do this as well. And so in the paper, they already have spectra here for warm dark matter, and they don't show the spectra, but they also give the case for cold dark matter. And again, there's a relation between the structural characteristic scale here and the particle properties and the cosmological parameters. So these things came together with the ability to do better simulations, came to an immediate result, which was the neutrino model didn't work. And that's because once you represent the initial conditions with the characteristic scales there and the correct spectrum, and you simulate to the present day, you have to take account of the fact that first things that form are big, so the nonlinear structures, nonlinear objects can only exist where something has collapsed. And so the galaxies can only exist in places where the neutrino distribution is collapsed. When you do this, you get pictures of what the galaxy distribution should look like these. It didn't look anything like the Center for Astrophysics Redshift survey. And so you immediately came to a contradiction that no acceptable combination of the cosmological and neutrino parameters, basically the densities, the power spectrum, and the time when the structure starts to form, so this is a time when structure starts to form, this is the strength of correlations. For the nonlinear regions, this is what you get. This would require a Hubble constant of 200. And even back then, people didn't believe the Hubble constant could be 200. So this ruled out neutrinos. So it's kind of interesting that almost immediately, once you could calculate the initial conditions, it became obvious that the dark matter couldn't be made of any known WIMP. And this was obviously convincing enough, people stopped worrying about neutrinos, even though, in fact, the tau neutrino wasn't ruled out as a dark matter candidate until the final oscillation measurements became available for the second mass squared difference in 2002 or 2003. So people immediately moved on to other more exotic candidates, which could be cold dark matter, and then things look much better because we no longer have a cutoff and you can get structure on smaller scales. So now, of course, we have our initial conditions exquisitely well. We don't even need them theoretically. We have them observed. And from the spectrum, as we see, we find out things about the dark matter. So one of the things I like about this is now we can see that at recombination, of course, the matter was dominating. And the observations require 85% of it to be dark matter. This is without reference to anything in the present universe. So just the microwave background observations require collisionless dark matter to dominate. So now I think this is a very small error bar. So I would argue the best evidence for dark matter is now not in the present universe at all, but in the universe at an age of 400,000 years. Certainly, it's not using any of the same information, so it's extraordinary that we get the same answer. The other thing you find is the baryon density, which is a small which is many times what you see today inside galaxies, roughly an order of magnitude. So it also tells us that most of the baryons today are not in the galaxies we see. Then we get neutrino masses. I don't know if this is going to hold up eventually at such a tight limit, which again show that the neutrinos indeed can be almost a few percent. So now if we want to go and ask how can we use the present distribution to find out more about the nature of the dark matter, then we again need to do modeling, but we now have to do it at higher precision. What was found immediately is that cold dark matter works pretty well, but now how far can we push it? So this looks very precise if you plot things this way, because you can see I've got 8 orders of magnitude on this axis and 14 orders of magnitude on this axis. So when you plot the mass function you find from simulations, the agreement looks very nice. Of course, if you take a smooth curve through this is just the abundance of nonlinear objects, dark halos, as a function of their mass. You can see we have things where you can get agreement to here at least 10%. So simulations now have a pretty wide mass range. You can get an agreement for a particular cosmology. But there are some things hidden here. For exactly how you define what you mean by a dark matter halo can change your definition of mass by tens of percent and shift all these curves. And how do you decide what definition of a dark matter halo in your simulation corresponds to what you can actually observe? That's a much bigger uncertainty. So getting this very precisely is only the start of trying to understand things. And an additional effect which came up just after Ursh's talk, that even going down to this mass, there's still 40% of all the mass in the universe is in lower mass objects, or maybe not part of any object at all. So if you do gravitational lensing, then clearly you need to worry about all the mass. So you need to assume something about where the rest of that other 40% is and how it's distributed to the parts that you do have some observational control over. And then the definitions here, once we start to be precise, are affected by baryonic processes. So these are exactly the questions which came up towards the end of Ursh's talk. So if you ask how well can we simulate the things we see, so this is our largest current simulation of the formation of the galaxy population. This is the successor to the Millennium Run. It's a dark matter simulation with 300 billion particles this is a cube of 4 gigaparsecs. When you use the stored data to simulate the formation of the galaxy population, you get a direct simulation of the formation of about 1 billion galaxies. And the resolution here is just sufficient to be able to get convergence to what was found earlier on a higher resolution simulation like the Millennium Run. So this is the number of galaxies as a function of their mass. This is the blue is what was found in the Millennium Run. This is what's got for the same galaxy formation model here, so simulating things in the same way. You can see you get reasonable numerical convergence. So now as a large enough simulation, you can ask how precisely does the galaxy population now actually simulated match the prediction, even for things on large scale. So here, for example, is how well you can see the baryonic acoustic oscillation signal. So this is the correlation function of different objects multiplied by various powers of r, 3 powers of r, and with the bias taken out. So you can see the baryonic acoustic oscillation feature, which you want to use as a standard ruler to do precise cosmology. What you expect in linear theory is the dash curve. It always looks the same. What you find in the simulation are the points for different galaxy populations defined to different densities, so relatively rare and bright objects here, more common objects over here, and defined in different ways, selected by their mass in stars here, or by how fast they're forming stars, which is related to their brightness or their emission line strength here. And what you can see is, first of all, the shapes are all different from what you predict in linear theory. Most of this is understood, but you can see they also depend on exactly how you define the sample. So if you want to use these to get precise results, you need to understand these effects at least well enough to get to the 1% or whatever level is needed. And the shifts here between the way you choose the galaxy samples are large enough that you might have to worry about them, for example, in Euclid data. So we need to understand these things well if we're going to get to high precision. We need to understand the baryons. And this is another example which is actually the same effect Ursh referred to. This is comparing the matter power spectrum in 2 simulations, one which had only the dark matter was followed, and the second which had now in a direct simulation of all the galactic physics using hydrodynamics of the formation of the galaxies, but from the same initial conditions. And what you take, this is the ratio of the difference in the power spectra to the power spectrum, and what you can see is on small scales, so high frequencies here, there's more power in the thing with the galaxy formation, but on this range of scales, there's actually less power in the galaxy formation simulation than in the dark matter simulation, and the effects are above 1% out to k's of 0.2 or 0.3 here. So this is exactly the point that Ursh was making. If you want to be precise using these things, then we may have to understand or at least calibrate these effects. It's not enough just to take what you see in the dark matter to get precise answers. So let me now come to the nonlinear structures, the details of the nonlinear structures, which is where we want to find out about the dark matter itself. So this is a very high-resolution simulation of a galaxy halo. This is a high-resolution simulation of a galaxy cluster halo. There's a difference in mass of about 300. So they've just been rescaled by a factor of 7 using a similar color scheme, and you can see they look statistically identical. What you see is they're both cuspy, and their radial density profiles are reasonably well fit by one of the standard fitting formulae. They're not round. In fact, they're typically triaxial. And the axis ratio of equidensity contours can be up to 2 to 1. And you see in the outer regions, you see a lot of small substructures. And again, the amount of substructure looks visually very similar. So once you scale out the overall mass, dark matter halos are predicted to look very similar on different scales. How similar? Well, not completely similar. So for example, if you take 9 clusters and you plot their density profiles, so this density is a function of radius, and you multiply by r squared to flatten out the mean trend, then you can see there is some scatter. So this is a plot where they've been scaled in such a way that if they were all exactly the same shape on a log-log plot, they would coincide, and you can see they don't. This tells you that one object to another, this is a significant scatter, which is no surprise when you look at all the fine-scale structure inside them. And what you can see is the scatter between these halos is significantly larger than the shift you get from the average for a cluster halo, which is the black curve here, and the average for a galaxy halo, which is the red curve, even though there's a factor of 1,000 difference in mass. So the changes in shape as a function of mass are really quite small compared to the scatter you get at any typical mass. On the other hand, there is a significant shift in mass, and that's not in the shape at all, but in the characteristic density of halos. As you go to smaller and smaller halos, they get denser and denser. And that's shown on this plot from the Aquarius simulations. This is plotting the characteristic radius against the characteristic velocity of dark halos. And we're going from galaxy scales up here, velocities of 100 kilometers a second and scales of tens of kiloparsecs, down to scales of 1 kilometer a second and a few tens of parsecs. And what you can see, these are simulation results. So this is just a convergence test to show that as you increase the resolution, you can go to smaller scales. So you can look at the red curve down to about here, which is the highest resolution simulation. So it's down to characteristic velocities of a couple of kilometers a second. And you can see there is a well-defined relation. This is the scatter about it. And it's steeper than this relation, which would correspond to constant concentration or constant density. And so as you go to smaller and smaller objects, they're getting denser, which means the mean density controls what their efficiency of annihilation is, if we're trying to look at their annihilation radiation. So this means that as we go down to smaller objects, they're more and more efficient at annihilating, if indeed dark matter can annihilate. And the smallest things you can see here have a mass which is about 100,000 times the mass of the Sun, whereas the smallest dark matter halos that we think may exist for a standard WIMP are about the mass of the Earth. So we have another 11 orders of magnitude to go down. So we have not been able to simulate yet down to the scales where actually most of the annihilation radiation would be coming from. If you actually look at how well the substructure forms, so this is the number of small objects as a function of their mass relative to the big object. So here we're down to small objects which are 1/1,000,000th of the mass of the big object, and this is just the count. And this is what you get for typical galaxy clusters. What you get for the typical galaxy halos, you can see they look very similar. So again, there's a slight shift, but basically they look very much the same. And and another interesting thing you see, if you count how much mass is in each decade of this, then you can find that by just multiplying by 1 power of n, you get a curve which is essentially flat. So that means each decade of subhalo mass contains roughly the same amount of total mass. So that means we don't know well how to extrapolate these 11 orders of magnitude. So it's still quite uncertain exactly how much in total is contained in little lumps. And since the little lumps are the ones that are doing most of the shining in the annihilation radiation, this means the annihilation radiation itself is also pretty uncertain. If you nevertheless try to go ahead and measure it, this is what you predict. So this is using the highest resolution simulation for the Aquarius series I was showing on. You can divide the predicted. So you imagine sitting 8 kiloparsecs from the center on a little planet going around a star, and then measuring what the simulation would predict the annihilation radiation should look like on the sky. So you can take the smooth dark matter density distribution. You project that on the sky, you get something which looks like this. It's very concentrated at the galactic center. That's where the highest densities are in the smooth curve. But now we have all the little lumps. And the little lumps are actually quite efficient at radiating, but most of the little lumps are at large distance because they're on the edge of the halo. So when you plot the radiation from the little lumps, you get a plot which looks like this, where there are lumps everywhere, but they're almost uniform across the sky. But then there are the 11 orders of magnitude which the simulation doesn't resolve. So if you extrapolate to ask what their radiation should look like, first of all, that's most of the radiation, and then it's also, if you assume they're distributed like the ones we can simulate, it's also nearly uniform on the sky. So actually, in these three plots, most of the flux is in this one. But it's nearly uniform, so it's very hard to see. So you add them together to get the prediction for the total flux. This is what you see. Most obvious, most of the flux is the broad distribution. The thing which is most obvious is the galactic center. And the little dwarf spheroidals or satellites, you can barely see them. If you look really carefully, you may be able to see one or two. So it seems strange when you look at this plot for that's what's predicted, that people argue that what you should do is go and look at the little galaxies. But the reason for that is that the main problem is getting rid of the foreground, which is the other sources of gamma rays. In the galactic center, there are all sorts of other things that might produce the gamma rays, whereas in the small satellite galaxies, not so much. So where the right place to look is to try and see the annihilation ratio depends very much on what you think the noise sources are that are going to contaminate it. So let me go through some possible issues with how the simulations are working, how these might affect our inferences about the nature of the dark matter. So do profiles look like NFW, or do they have central cusps? What can this tell us about the nature of the dark matter? So I already showed you the simulations. Here's one example of how well they fit real data. This is 10 galaxies. This is lensing data to measure the strength of the lensing as a function of distance from the center. Here are the observations. Here's the prediction. You can see it's fitting quite well. It's clearly not a good fit to this power law. So that's, you can see that the nonlinear structure does appear to be similar to what's predicted. If you ask in more detail what's predicted, it's actually quite surprising. So if you ask what's the profile, the average profile of a dark halo supposed to be to a large radius, what I was showing you before was this is the mean density. This is a function of distance from the center. A rich cluster like one I showed you was correspond to the highest mass curve here. And this is just from a simulation, stacking the simulation. What you can see is at large radius, you actually start to see the other objects on average. What's curious is what happens as you go to lower mass halos. So you stick something which is like the mass of the Milky Way's halo, which is about kind of like this the cyan curve here. Here's the NFW or an ASTO profile. And then when you start to see the other galaxies, on the average, you expect to see a curve which has a sharp feature here. And so what you can see is the inner parts are fit by the profile standard fitting formulae. What you get at larger radii looks like the linear correlation function because you're seeing the average effect of all the other galaxies. And the transition is actually quite sharp. So this is something which is predicted by our dark matter models. So the question is, can this be seen in data? So here's preliminary results from a study using the SDSS. What's been done is to take galaxies which are brighter than any other galaxy near them in the Sloan data and stack the lensing signal around these galaxies. So these are the most massive galaxies here. So these are the central galaxies in clusters, the least massive galaxies here. And then the points are the actual lensing data. So if you now take a simulation which has matched the galaxy clustering, where you've actually simulated the formation of the galaxies and you've tuned it to match the spatial distribution of galaxies, then this becomes a no-parameter prediction because you've already fit all the parameters of your simulation. You can ask, does it predict this lensing signal? And using a WMAP7 cosmology, these are the predictions. So you can see that, particularly for the more massive systems, which are less noisy, they're pretty good. The shape is there. They're a little bit low. And you can see the prediction at the lower masses, you see this kink. So it is predicted you will be able to see this kink. So this is preliminary. We don't know the answer. One of the interesting things, though, is if you rescale the simulation so that it's no longer WMAP7 but Planck, you get this. Okay, WMAP7, Planck. So you learn two things. First of all, it is actually sensitive to the cosmology, so we should be able to get this. And at least at the moment, the Planck is fitting slightly better. I'm not sure this is going to hold up, but we'll wait and we'll see. When we finally finish this properly and track down all the other sources of error, maybe it'll go the other way. But there is sensitivity here. And what you can see is the error bars on the data are really getting quite small. So I think, as Orosh was saying, this kind of information really is going to help us to learn things about the cosmology. One of the curious things about what's happening with our cosmology, if you ask how it affects the large-scale structure, the way this was done was to take the Millennium simulation and rescale it so it becomes as good a representation as possible of the structure in a neighboring cosmology. So, and to do this, what you have to do is you reassign the size of the simulation to make its linear power spectrum as good a shape, as good an approximation to the shape of the one you want over the range that gives rise to the nonlinear structure. So that means changing the size of your simulation box. And then once you've done that, you have to change the mass of the particles so that the total mass in your volume is about the same size. And then you have to reassign redshift so that the amplitude of the linear power spectrum is correct. And once you've done all that, you actually find you're very close to it. So it's curious to see how you have the original Millennium simulation was done in the WMAP1 cosmology, so it had a box size of about 680 megaparsecs and a particle mass just above 10 to the 9. How you have to do this scaling in order to represent the different cosmology we've gone through. So after we run the simulation, WMAP3 came along, and you had really, it's quite far off. It had to be down here. You had to make the box about more than 10% smaller and change the particle mass. But then WMAP7 came along, well, 5 first, and then 7, it moved up the other way. And now Planck, it's moved back here. So you can see we're kind of going around a cycle. So the point of view of the large-scale structure, none of these things has moved very far. And actually, Planck is closer to WMAP1 than any of the other WMAP announcements. So actually, WMAP9 is also now very close here. I didn't put it on this plot. Let me come to the central structure of galaxies. We heard about this from a couple of people earlier in the meeting. So is it possible that the structure of the dark matter at the center of nonlinear objects can be telling us of the dark matter distribution, can be telling us about the nature of the dark matter? And this is a long-standing debate. So here's one of the most recent results on this particular topic. So this is using the toroidal galaxies, so one of these very small satellite galaxies around the Milky Way, which has only about as many stars, or a few times more stars than a globular star cluster. And using the stars of different stellar populations, which have different distributions inside the galaxy, to measure the mass in a robust way at 2 different radii. So effectively what they do is they take metal-rich stars and metal-poor stars. The metal-rich stars are close to the center, but both populations are presumably sitting in equilibrium in the same potential well. So you try and find a robust estimator for some mass at some radius from each population. And so you can measure pretty accurately the radius that contains half the stars in projection, and you can measure the RMS velocity dispersion of the stars, so you can construct a mass this way, and then if you take the right coefficient, then this turns out to be a pretty robust estimate of the mass inside the radius that in 3 dimensions that contains this half of the light. Okay? Now you do this for 2 populations, you get one value up here with some uncertainty and one value down here. So you can ask, okay, so I know the mass in this radius and I know the mass in this radius. Is this consistent with a cosmological profile? and the curves predicted by the kind of simulations I show you have roughly this slope. So if you shift this curve down to go through here, it'll miss this one. If you shift it up to go through here, it'll miss this one. So what this seems to be showing is that the mass is increasing with radius significantly faster than predicted by the cosmological halo. But it does assume that this coefficient is the same for both populations. What should we do? So there are 2 aspects to this. So what this means is there's less mass in the middle than you thought, so that means the density is not increasing as rapidly. This is what's usually called a core. Maybe the density has actually been going constant at the center. And it would have to be a core with a radius, as you can see here, of a couple of 100 parsecs. Right, somewhere in the middle here. Or bigger. So there's 2 points. First, the question is, well, does this tell us about the nature of the dark matter? or could it be telling us about baryonic physics? And the second question is, well, how robust is the argument? Is it really true that we can't find something which fits the data where the actual mass is following this curve? So let me go to the first point. So there have been a number of simulations showing that if you follow not only the dark matter distribution but also the evolution of the distribution of stars, the baryonic process is basically the gas condensing into dense regions until it can make stars, and then the stars forming and blowing up and blowing material out again. The gravitational effect of this process can change the dark matter distributions, and it tends to change it in the sense of pumping energy into it, which means it moves the tightly bound central part outwards a bit. So it reduces the central densities. So these are simulations by Zolotov and collaborators, where they looked at satellites in a Milky Way simulation they'd done, and they had a dark matter simulation where the satellites had density profiles. So this is log density, log radius, which looked like this when there was dark matter only. When they looked at the same object, when they ran the same initial conditions, now with the other physics in, they found things which were significantly affected. The total mass went down, and the shape in the center changed. And that's as a result of these kinds of processes. And what they found is where they had things with a lot of gas and a fairly large number of stars, these effects are quite big. So you can see these two panels. These are luminous objects which are either gas-rich or gas-poor at the end. And as long as they're luminous, that means they have a lot of stars. So these effects are quite large, and they see a significant suppression. If they take the smallest objects, they just had so few stars that even though star formation went, it didn't really change things much. And here you can see they didn't see much. So the question for the dwarf spheroidals in this context is, they have so few stars, could the activity really have been enough to change the dark matter distribution? And that, I think, is not clear. To me, for the very small objects, it seems a bit implausible. The second question is, do we believe the result? So here are models where the profile is exactly the profile that you would expect. The density, the mass, the potential well is exactly what you'd expect from one of the simulations with the parameters that would be expected. And we've just tried to find distribution functions for the stellar populations in this which match the data as well as possible. You just search around to see how well you can do in a fixed potential. And this is how well you can do. So this is a particular potential well. This is the number of stars as a function of distance from the center for the metal-poor population and the metal-rich population. And this is the measured velocity dispersion for the metal-rich population and the metal-poor population. And this is just a model you found by searching around a bit. And what you can see is these, in a chi-squared sense, these are good enough. The chi-squared is order 1 per degree of freedom. So, are we going to change, is this so bad that we're going to change our view of what the dark matter is? It seems to me, I'm not convinced. What about the shapes of the dark halos? I have a slide here, but I think I'll skip it. The idea is the models predict the dark halos not to be spherical. Can we see that? We can see that perhaps through gravitational lensing, but in the Milky Way and in Andromeda, we can see streams of stars which are moving through the halo, and perhaps we can use the dynamics of these streams to constrain the shapes. And this is quite active. I think there's still some controversy about the results. Is the substructure as predicted? Everybody, I think, now has come to the conclusion that the substructure has very little dynamical effects on the stars we can see in the galaxy. For example, the structure of the dynamical disk, of the disk. But it may have some effect on the other things, like lensing, the lensing properties of galaxies, if you happen to have a right kind of alignment, or even on the dynamics of these same streams. So here's an interesting argument. So these are counts of stars in a very large part of the sky. From here to here is 200 degrees on the sky. So this is a very large region of the sky, and these are counts of stars. There's a globular cluster here, and you can see right along the middle here, there's an excess of stars, which are stars which have been tidally torn off this globular cluster as it goes through the Milky Way's potential. And if the halo of the Milky Way is not smooth but has lumps in it, those affect the structure along this stream. And you can show from simulations that introduce gaps in it. And it's claimed that there are 5 significant gaps along this stream. So this is, we're used to strange statistics in cosmology, but this one, I look at this, it seems to be all gaps. But anyway, the claim is that there are 5 gaps along here with 99% confidence, whatever that means. And this requires a large number of substructures. So I think, I'm not convinced by this argument yet, but it looks to me as though it is an interesting possibility. There is an effect that these structures, which are very thin and very coherent, could be affected by very small lumps in the Milky Way's halo. And so this may eventually show us a way to measure them. So let me move on to dark matter, to whether halos structure could be affected by warm dark matter. So here, this is a simulation of a Milky Way galaxy with cold dark matter. And here is whether what's the authors here, this is a Durham paper by Mark Lavelle and collaborators, is what they call a 2.3 keV sterile neutrino from the same initial conditions. And what you can see, there are far fewer substructures. Basically, all the small substructures are not there because the free streaming in the initial conditions got rid of the small-scale structure in the initial conditions. And they claim in this paper that you have to have a mass of at least 1.5 kilovolts, otherwise you don't get enough substructures here to actually account for the number of satellite galaxies we see around the Milky Way. So eventually, when they published this paper, initially they were going to have a measurement of the dark matter, but when the paper finally came out, they quote this as a lower limit. Here's some density profiles. These are halo substructures. So one of these is a cold dark matter subhalo, and the other is the same subhalo seen in a warm dark matter. Notice they all look very similar, and none of them show a core. Warm dark matter does not predict cores in galaxy halos on the scales that are actually being measured. This is something which I think a large part of the community that's not on this field does not understand because it's improperly presented by many of the people who are doing this work. They claim that if you see a core in a dwarf galaxy, this shows that perhaps that warm dark matter is the correct solution. This is not true. The cores seen are much larger than were predicted for any of the warm dark matter masses which are viable. What is predicted in warm dark matter is a density profile which is slightly shallower than in cold dark matter, but you don't see any deviation. You still see a cusp. So you take the ratios here, you can see the ratio, this is the ratio of the warm dark matter profile to the cold dark matter profile. So this is the most massive warm dark matter particle, has the least effect. Even at the smallest radii, the effect is quite small. It's 20%. So the effects are quite small. So if there are cores in these dwarf galaxies, warm dark matter is not the solution. What it does do is shift the mass inside because the shores become, so if you take a halo of a given characteristic velocity, it corresponds to a larger mass in a warm dark matter universe. So maybe this will mean that the halos that we see, if the universe really were warm dark matter, of the satellite galaxies are somewhat more massive than was inferred in a cold dark matter universe, which might affect one of the problems that people have discussed recently, the so-called too big to fail problem. But the final point that I want to spend a little time on is the fact that I think that actually warm dark matter at a level that would affect galaxy structure has already been ruled out from this Lyman alpha work, not this Lyman alpha work, from Lyman alpha work similar to what Orosh was talking about. And as Orosh mentioned, you can use the diffuse intergalactic gas seen in quasar spectra by taking its power spectrum. You can actually measure the power spectrum of structure in the universe at these early redshifts, all the way from 2.2 down here to redshift 4.2 here in this McDonald paper that he referred, well, it's related to the data he referred to from this earlier Sloan data. And this is what the data are the symbols, the measured power spectrum, and the model, the cold dark matter model, the colored symbols, you can see is an amazingly good fit. So if you can now extend this to smaller scales, then you can actually measure the power spectrum. And what's predicted, the linear power spectrum, notice there's only a factor of 2 on this axis here. This is the power spectrum, there's a factor of 100 on this axis, so this is very stretched. This is the suppression in linear theory is predicted to be this shape, this green curve, where for a 2 keV particle it's where it's shown. If you have a lower mass particle, it moves to the left, and a higher mass particle, it moves to the right. Nonlinear effects, though, modify this. So the other curves here are what you expect in the nonlinear regime through direct simulations using hydrodynamics. So for example, for a 1 keV particle, at a redshift 5, this is a predicted power spectrum. So you see it's suppressed significantly here. At redshift 3, it's much less suppressed because nonlinear effects have actually filled in some of the high frequencies. So you need to do the simulations to make this effect. So the SDSS data was sensitive in this direction. High resolution data are sensitive about a factor of 5 smaller scales. You get to the regime where correspond to the masses that we're interested in. So what the effect this has on the spectrum is with the cold dark matter, you get the green curve. With warm dark matter, with a 1 keV particle, you get the black curve, and you can see there's less high-frequency structure. So this, if there were no intergalactic medium, this would be 1, and this is absorption. So at these points, the absorption is complete. So the result from the work here, this is work by Field, Becker, Bolton, Hainault this year. Here are the Sloan data. Here are the high-resolution data. And here are the predictions for a 2.5 keV thermal relic. What you can see, it's substantially under-predicting the effects you see at the highest redshifts and at the smallest scales. So the claim here is that they have a 2 sigma lower limit on the mass of the warm dark matter particle if it's a thermal relic of 3.3 keV. If you go back to the work I was showing you before and you translate to the same definition to a mass that corresponds to the same power spectrum, and you find this means that the effects on the satellite distribution be much weaker than any of the models that I was showing you before. So with this limit, then it's sufficiently large that warm dark matter will not have any significant effect on the structure of any visible galaxies, even down in their core. So let me conclude. So I think there are lots of things I didn't have time to talk about. I think you can worry about constraints on annihilation for other kinds of effect. For example, dark stars. Can dark stars work? That's the stars which are powered by dark matter annihilation. This requires simulation. It's not been simulated reliably yet. What about if there's a self-interaction between the dark matter, which on small scale, which makes it collisional? There's been some work on this, and there could be constraints on this, but it's actually been relatively little simulation recently. I think for more extended dark matter models, this is definitely worth following up. There's some work also on what happens if you make your dark sector physics more complicated by introducing dark matter, dark energy interactions. So these interactions which affect the dark matter but not the baryons. This leads to force effects. You can have a different effective gravitational constant for the baryons and the dark matter. This leads to effects which appear like a variable dark pattern mass, because effectively the dark matter energy is being transferred into the dark energy. Or you can even, or you can look for simpler effects just of the dark energy on the modification of the structure of dark matter halos, just to do different assembly histories. And again, there's quite a lot of work here, but I think at the moment it's not at the level that, first of all, there are a very large number of models, and secondly, there are a relatively small number of people working on any one of them, so the work has not yet got to the same level of exploration as things on the standard model. So the takeaway messages, I think, is although it was easy to rule out neutrino dark matter immediately, once you could predict what it should do, cold dark matter has actually been reinforced so far by the simulations, and the effects we're looking at now are actually quite subtle. So to see differences in the dark matter distribution, we need to simulate things at a much higher level of accuracy. So I think for most effects, the simulations for many purposes, the current simulations of the dark matter distribution are actually limited by uncertainties in the baryon effects. So the nonlinear structure is mostly, the uncertainty in what we can predict for the problems we're interested in is limited by how well we can treat the baryons. And the apparent small-scale discrepancies that people are focused on to do with the inner structure of satellite galaxies or the abundance of structures actually don't really have the characteristics expected for warm dark matter or most of the other modifications that have been suggested. And the Malaya alpha forest data now seem to exclude warm dark matter which, with a mass which would actually have interesting effects on the observed galaxies. So there are many more things to look at. So I think, I think in the future we may well learn about dark matter properties from simulations, but I think at the moment the cold dark matter model is still doing very well. So I'll stop there.
Thanks, Simon. Do we have any questions? Just wait for the microphone.
Simon, I have a question about dark matter annihilation prediction. You show a plot where the number of subhalos scale like 1 over mass, basically. So if I take that seriously, that suggests the integrated signal, the dark matter annihilation signal to scale roughly logarithmically with the mass resolution.
Oh, it's worse than that, because the smaller halos are actually more efficient at creating annihilation radiation, so it's worse than logarithmic.
So it's power law, you're saying? Yeah. I see. What is that power from what you can see?
It's quite weak, so if you actually extrapolate down to Earth mass, it dominates in the outer parts, but it's still negligible in the inner parts where we live.
So even logarithmic suggests already a factor of 10 uncertainty.
Yeah, that's why in the plot I showed you, the diffuse part from the unresolved subhalos was actually the dominant contribution, even though most of them are 100 kiloparsecs away from us.
Do we have one more question?
So, Simon, I mean, the discrepancy in the amplitude of the fluctuation spectrum from Planck clusters and other cluster analyses and the primordial CMB is about a 10% effect. So, you know, are there any other tests other than weak lensing that you think can constrain that amplitude to high precision?
I think my current best bet for the source of the discrepancy is actually sample selection effects in differences between the samples of clusters which are used to calibrate the relations you need to convert observable properties to mass, because these are typically calibrated on clusters that are well observed, which tend to be big, regular clusters. Whereas when we apply it, we want to know the abundance of objects per unit volume down to some fixed mass, because that's what we predict cosmologically. And if you take a mass-limited sample of clusters in a cosmological volume, only a fraction of them are actually well-structured regular systems, and a lot of them are less regular. And the less regular ones tend to have less X-ray emission, less Sunyaev-Zeldovich signal, and so on. So I think there's a chance there's a significant bias between the population of clusters that we actually measure these relations on and the population of clusters which we want to count per unit volume. This can significantly shift the relations. But to calibrate that, it doesn't help to go and look at the well-observed clusters over and over again and measure their men's of the lead, because if you have a bias subset to start with, no matter how, the problem isn't you've measured the masses wrong, it's you've measured the wrong clusters. So that part of the bias, you have to get appropriate volume-limited samples of clusters, and it has to be volume-limited by mass, whatever mass definition you're using to calculate the abundances. And that's not so easy to construct.
I mean, we can test that already with hydro simulations.
Yeah,
that's
right. So I think the weak point of my argument is the current hydro simulations seem to suggest this is not a big effect. But on the other hand, we do see clearly in the data that if you split the data according to the more regular and the less regular systems, you do see shifts. So I'm not convinced that the current hydro simulations are telling the full story.
Okay, great. Well, let's thank Simon again for a wonderful talk.